Yeah, today we will finish how to compute expanding balance separator fast, right? And just to recall what we want to show is this, right? We want to show that given any graph, then with high probability, we can compute 1 over log square expanding balance separator. Okay? And the time is something like Polylog max flow. Okay? And like we kind of reduce the problem to the following. We look at split graph. I think you remember this. Okay? And we say that, okay, we just reduce the problem to this one, where here the subroutine is that you are given a balance separator, F0, F0, right? And there is a subroutine called expand or shrink that given G and or F0, then it compute another balance separator, which is either expanding and we are done, or it reduces the size of F0 to something smaller by some constant factor. And if we can do this, then we can get the balance separator just by applying this again and again when you initialize F0 with E, with the whole A set. Okay, so now to solve this one, we will again recall that we're gonna use max flow, right? And just two quick thing about max flow again. Given about flow, about single commodity flow, is that given any flow, if the flow routes some demand from the source to sink, then you can basically extract a bipartite graph M, where one side has no degree source and another side has no degree sink. And this bipartite graph is routable in G. And the size of this bipartite graph is at most the number of edges in G. So given this flow here, you can extract the meshing or the bipartite graph that this flow F routed. Okay. Okay. And another picture is just this one. If you have some source, you have some sink, and you compute max flow, then you get two sides of the flow. The flow before min cut and the flow after min cut. And the flow before min cut basically saturate everything along the cut. Okay? It sends flow from the source to saturate the min cut. And from the min cut here, for the flow after the min cut, it saturates the source before, after the min cut to some sink. Yeah. So that's a picture that you should have in mind. And another thing that I want you to recall is cut matching game with deletion and transferring vector. Okay. So, okay. So just very quickly, how does it look like? In this game, we start with some empty graph, right? And then there's going to be some active set, which we initialize to be the whole vertex set. And then, in each round, the cut player will choose AI and BI from the active vertices. If this is a graph and this is active set, then AI and BI is something inside the active set. Okay? And what will happen is that the meshing player will choose deleting set, transferring meshing, and mixing meshing. So in picture, it looks like this. Do I have picture? Yes. Right. The meshing player will choose some node in A to be deleted, and then it's gonna choose this thing that which we call transferring meshing, right? Which basically kind of move this A from to A2 in a sense that this guy used to be active, this guy was inactive. Now you can just transfer vector from A from to A2, and this will become inactive after this round, and this will become active after this round. And once you transfer the vector from A from to A2, then like this thing become like kind of your new A. This is like A prime I, let's say. And then the mixing meshing will basically mesh everything that is in A prime to B, right? So the requirement is that everything in A prime need to be meshed. Okay. And this is one round in cut matching game with deletion and transferring vector. And okay. And do you remember what we say, like what's the guarantee after log square round? What do we say? What's the guarantee of the cut matching game? Okay.
Union over all matches is I think it's like 1/2 flow expanding.
So like union, let's say there are R round, number of round. So this is like a union of all the meshing, which is both the transferring one and the mixing one. Okay. So this is kind of expanding in some sense, but in what precise sense? Like there is some node weighting that is expanding in this graph. What's that? Indicator of what?
The active.
Exactly. The indicator of the active set. Like, so active set, like you know, like active set, you initialize to be everything, but after each round, right, you delete something, you move something, so the indicator, the active set change through each round. And we want to say that the indicator, like the active set at the end, is something like expanding in this thing with high probability. Okay? So this is cut matching game. Okay. So now we are ready to what? Okay, good. Okay, so by the way, like what we show is that there is a way for a cut player, right? Such that when the meshing player can delete something, if the meshing player can delete something and transferring vector and transfer the vector, there exists a strategy for the cut player such that it chooses AI and BI in time like NI, such that first of all, AI is not too big. It's kind of quite small actually. And BI is big. And yeah, at the end, this is expanding. Okay, good. So now we are ready to now we have all the tools. We will now like show you how to compute this thing, like to solve this problem. This thing. What? This thing. Okay. So let's see some animation. So by the way, like the idea is kind of similar. Like we will first kind of, maybe I use the animation that I prepare. Okay. Oh, good. So let's see the algorithm. There will be iteration. Basically, in each iteration is to simulate one round of cut matching game. Okay. So first of all, there is our graph. This is our graph, input graph. And there's going to be another like kind of cut matching game graph, which is, this is just for cut player. Right? And I have this graph and recall that like if this graph has edges, then we can recall this notation, right? This is like a split node of like we are given the graph and some initial balance separator, right? F naught. Let's say it might look like whatever, something like this, right? And then our graph X here is just empty graph, but the vertex set is just the split node for each edge in F naught, right? This is like for each edge on this thing, you create a node for X naught. That's the vertex set of X naught. Actually, no. Let me actually use this. It should be split node for every edge, actually. For every edge, we create split node for it. Okay. But it's just that the first active set is going to be the active set for F naught, like the split node for F naught. So the first active set is now like not everything. It's just some set here. Okay, and let's say we are at round I. Okay, so at this point, we will keep updating our balance separator F. It will update to some Fi minus 1. At every round, Fi will be always balance separator, but it just keep updating. Okay? So at this point, this is our balance separator. And our active set will be the split node of this balance separator. We maintain this at all time. Okay. And what will happen in this round? Well, first, the cut player will choose some AI and BI. Okay. So it's just going to choose some set from the active set, AI and BI, left and right. Okay. And then what we will do is that we will kind of try to send flow from AI to BI. So we look at this, like we kind of look at this thing, look at the split node for each of the, like for each node, for each split node in AI, we just kind of look at the corresponding set here. And then we let the source to be the indicator of the split node of A. And the sink is just indicator of split node of B. So we try to send flow from A to B. And so then we just try to send this flow. So we call this max flow min cut in split graph, right? That try to send flow from A to B. Okay. So we do that. Yeah. If we succeed, if everything just send, then we if there is no bottleneck, then we just get some flow. Everything in A will be sent to B, and that will correspond to a meshing, normal meshing that match everything in A to B. So that would be good. That would be easy. But it might not be the case, right? You might get stuck, as in the flow might find some non-trivial min cut. So maybe the non-trivial min cut look like this. Okay. So let's say that there is this edge here. Like there are just 3 edges along this cut. Then maybe this is a split node corresponding to the edge along the min cut, crossing the min cut. Okay. So now what we will do is this. We look at the flow. We look at the flow that define like the flow before min cut and the flow after the min cut. Okay. The flow on the left and the flow on the right. Okay. Okay, so what you know is that, well, all edges along the min cut will be saturated from the left and from the right. Right? Okay, so now it just kind of create, like we will now like try to kind of proceed in this round by defining like deleting set and transferring matching and mixing matching. Okay. Okay. So the idea is that I will just define the transferring matching to be kind of just to correspond to the flow on the left. Okay. So whatever this, like this guy kind of gets stuck, it kind of gets stuck at the min cut, but it can like these are the guys that send flow to this cut. So I just create this transferring meshing. Okay. And then, there should be this thing too. Yeah. And the mixing matching is just the flow after min cut. Okay. And what should be my deleting set?
The ones that didn't get matched on the left.
Exactly. Like this one, you didn't match them. So like we should just delete them. Okay. Okay. So that's how like then we just say that our new graph X is just a union of this matching, these two matching. Okay. And our new separator will be like we just gonna like what is good. Our new separator, balance separator, will just basically, remove the thing inside here, and this is kind of become new thing in the separator. Okay. So we add edges along the cut, right? And whatever separator edge is inside our min cut, just remove it. Okay. And you see that we can justify active set in the same way. Like its active set is just gonna look like a split node of the new separator. Why? Because like this guy we delete, right? And this guy we basically move to this one. So the new active guy is just like it's just gonna naturally move to the new active set, just correspond exactly to the new separator. Okay. Question about what's going on here?
So what if we have something like the picture you were showing earlier where the left set kind of encompasses part of the
Good. Yeah, let's we will basically ignore that. So suppose that I have like, yeah. Suppose I have this graph, and then maybe this is my, some balance separator. This is like a F(i-1), and maybe this is like maybe this is my kind of AI, and this is my BI. And what you ask is like, what if my cut look like, let's say, here. It contains something here, right? And let's say that this is like a cut edges. Okay. So what will happen? How we plan to update? Actually, is that let me create some node weighting. Okay. So what we know is that like the flow on the left will saturate the sink on the left. What is the sink on the left? It's cut edges and here. Right? So you will have some flow, maybe this guy, and maybe this. Okay. So here actually the way I'm gonna define my deleting set to be, I'm gonna delete this guy and also delete this guy. This is my DI. Like, because the way that we define new FI is just actually like, it's just F union the cut, and we remove F intersect L. So like only this guy become active, and like this guy will be not active anyway. Like this guy will not be in my new separator anyway. So I can just delete them too. Yeah. Right. Okay. Yeah.
So you can delete from both A and B?
Yeah.
Can you transfer from us? Like, can you do transfer on B as well, or?
No. Actually, yeah. So good point. So in the definition of cut matching game that I say, I just say delete only thing in A, but it's okay actually to delete things in B too. Yeah. As long as you know that it will not match. It will not be matched. Yeah. Okay. More questions? So what I hope you to be convinced is that if I define like my matching, transferring matching, and mixing matching, and deleting set in this way, I really kind of just simulate one round of cut matching game in the X graph. In like from the perspective of cut player, like the matching that we provide, like we compute some flow and we provide this transferring matching, mixing matching, and deleting set. The thing that we provide to cut player, from his perspective, just look like cut matching game. Which means that like after log square round, the active set must be expanding. Make sense? Okay. So okay. So what I described to you is not, there is something that is not complete, which is this case. So let me repeat again. There's like I start my X to be the split node of everything, and I let like okay. The active set is just this thing, okay? The initial active set. And we have log square rounds. In each round, the cut player choose a disjoint set from this active node. Note that this is just correspond to active nodes. And yeah, and I compute the flow. I compute max flow min cut from this flow instance that we described. We get flow on the left, flow on the right, and the min cut. Now there's one case here that I didn't describe. So far I kind of just said that what if like if L here, if this thing is like has size less than half, then if we update it in this way, right, then you get balance separator still, because the new component is still less than half. But it can be the case that this is more than half. Okay. In that case, we would just do it in the natural way. That is, I just gonna kind of, so suppose that this is actually big, right? So what we're gonna do is just, maybe I just draw it again, yeah. Suppose that actually L looks like this, Li looks like this. So what we're gonna do is just kind of take this as a separator and forget everything here. And so our new separator is like, it's just defined to be Fi minus 1 plus the cut, but then remove this side. Okay. So then this is going to be still a balance separator. Okay. And in this case, actually just going to say that I'm done. I don't proceed anymore. But the claim is that if this actually happened, then if this case happened, then the size of balance separator actually shrink a lot already. So we can just say that it's a shrink case and we are done. Okay. But otherwise, in the normal case, when Li actually is like less than half, then I just do what I just described. Okay. So this is just some formal thing, but like it's just the picture that I drew. Okay. Okay. And then after log square round, I just return this separator. So, okay. So, yeah, what I need you to convince is just, yeah, all these things that we provide to the cut player is a valid move for the matching player. And the active set is gonna be always like the split node of the separator, of the balance separator. And if this is the case, if we guarantee that, if the cut matching game guarantee that at the end, indicator of active set is expanding in XR, it would mean that with high probability, the indicator of our balance separator at the end is expanding in XR. Okay. So are you convinced about this? This is like the first step to be convinced. Good. Okay. So now what I just need to tell you is like, if we get to string case, we actually we want to show that the size indeed shrink a lot. And if we get to expand case, then Fi is not just expanding in XR, but it's expanding in G. Okay. Okay. So, good. So if Li is more than half, if this is the case, yeah, actually I don't need this. This is always true. Yeah. Okay. So why this should be the case? Okay. Okay. So maybe yeah, the proof is just really short actually. Okay. Maybe I can draw, or should I? Yeah, I can just follow this thing. So what do we know? We know that if you look at the good, yeah. If you look at the floor, let's say this is L, right? And we look at the floor on the left, yeah? Then we would basically saturate it. And, okay, and if this is a I, and maybe this is BI, right? Maybe AI and BI. Good. So we know that the flow on the left here, right, basically saturate everything in the card and also saturate the node weighting of the sink on the sink on the left too. There can be something that is not send flow, that doesn't send flow. Okay. So this is like a source, this is like a sink. Source on the left and sink on the left. Okay. So we saturate this thing and the flow respect this thing. So this is smaller than this one. Okay. So it just give you this one. Okay. The size of this thing is smaller than the size of this thing. Okay. So now, what do we know about this? We know that the way that we define Fi, right? Fi is just this one, this is my fi in the string case. So it grows by this much and it shrinks by this much. And what I want to say is like, the thing that it grows is grow by a bit, but the way how much that it shrink, it must shrink a lot. Okay. And if that's the case, then it like in total it must shrink so much. Okay. So if I grow from fi minus 1 by this part, yeah, but this is just less than the size of A. Why? Because you even have like the cut size plus some sink is less than A intersect Li. So like the cut size must be less than A. But you know that A is smaller than like the active set over like 8. This is like you remember like this is like kind of the guarantee from our cut player. The cut player guarantee this that the A size is not too big. This is where I need it. Yeah. By cut player guarantee. So the cut player will return A that is not too big, and at the end everything still works. Okay. So this is like how much it grows here is just like 1/8 fraction. But I will say that how much it shrink will be a lot, much more than 1/8 fraction. All right. So how much does it shrink? Well, it shrink by this much, right? So maybe I just say that this is maybe my Li, right? But basically, like this is maybe Ai, but Bi must be really big in terms of node weighting. Yeah. Bi is big. Like Ai here is small, like it's smaller than 1, but Bi, right? Bi is big, bigger than half. Okay. And like the idea is that you see like we're gonna basically remove, like after we update the separator, everything in here will be removed. So like a lot of things like this big set basically is removed from our separator. That's why it should be like it should shrink a lot. So let's see exactly what happened. So actually B can look like this too. Like B can look like yeah, it can go like this, but B is still big. Yeah. So F minus L is at least B minus L, just because B is a subset of the active set, which is this thing. And B minus L is just the size of B minus the size of B intersect L. Okay. So the size of B here is just the size of the whole B minus the size of B intersect L. Okay. But you see, the size of B here is at least half. Okay. This part, like this whole thing, is at least half. How big can this part be? How big can this part be? Well, like this part must be small. Why is that? Like formally you have this thing, right? Here, this part is smaller than this part. This is just the same thing here. And this is less than AI, which is less than f over 8. So this part is less than over 8. But there is a way to see this formula like kind of intuitively too, because like you know that A is less than is less than 1/8 fraction, and like everything in here must be saturated by A. So like this part cannot be bigger than this part. That's it. Yeah. Okay. But then this means what? It means that like it shrinks by this much. It grows by this much. So the size of Fi is just gonna be the previous size is at most this minus it grows by this much 1/8 and it shrinks by this much, so 2 and 1/8 here. Okay, so at the end this is less than what? Maybe 3/4, right? I think so, yeah. Make sense? Okay. So the idea is just that if we decide to update our separator and remove the thing on the B side, we're just gonna remove a lot. So it's gonna shrink by constant factor. Okay. But normally we're just gonna update by removing the thing on the A side, on the L side. Yeah.
So I guess the intuition for why it has to shrink if we have a big cut is we know the cut is at least half the graph. We know B also has to be large, but the overlap has to be small because the overlap is saturated.
Yeah. So you mean the overlap? By overlap, you mean this thing?
B and the cut.
Yeah, right. The overlap need to be small. Yeah, because the overlap here is saturated by A, and A is small by the promise of the cut player. So this part is small. This part is actually big. So we just gonna still remove big part. Okay. Good. Okay, now what about so now I just need to show that FR actually is expanding in G. We convinced that indicator of the split node of FR is expanding in XR. This is just by guarantee of cut matching game, right? But we want to say something about X. But this is kind of the same reasoning now. Can you say why this should be the case? This thing is 1/3/8 expanding, but we want to say that basically the same thing is something like 1/log square expanding in G. Why that should be the case?
Because XR is essentially the matching, it will be a subset of G, right? Because it is the matching of the of the nodes that you select from.
Yeah. I think you get it. You get the idea. XR is not subset of G, but XR is smaller than G in one precise sense. What is that?
It kind of represents a subset of the edges.
No. So, like
XR is what the cut player sees, and
XR is smaller than G in the flow sense, right? You know that XR actually can be routed in G with congestion R. So you see, like, it's certainly not a subset. It's like it has different edge set, but every edge in XR can be routed in G with low congestion. Why this is the case?
Because edges in XR correspond to routable flows in G.
Exactly.
From the method.
Yeah. XR is just a union of like something like 2R many meshing. It's like XR is just union of mi prime and mi from I up to R, right? But what do you know about this guy? This guy, even union with M, with even like these two together, what can we say about like this and this? It's just routable in G. So I can just write this thing in G split. Yeah. Okay. Maybe I should say this. Are we clear about this? This is, yeah? Because this is just like, it's routable by the flow, by our max flow. Like this is flow on the left, this is flow on the right. So together, like congestion in even union, this is just one. You can route this in here with congestion one. But then like XR is just union of R many things here. So the congestion to route XR in G prime is just at most R. Okay. So if you can, given any like demand that respect this edge set, right? Respect the balance separator. You can route it in X with low congestion, but X can be routed in low congestion in G prime. So it must be like, so you can just say now that like any demand can be routed in G, like FR respect any demand can be routed in G prime with low congestion too. Okay. So, yeah. So XR union of this is routable in the split graph with congestion R. So, and we know that this thing, like, but this thing is flow expanding in XR. XR is routable in G prime. So this thing is expanding in G prime with this expansion. Just this thing, and you get worse by a factor of R. Okay, but if this like split node is expanding in split graph, we know that then the edge of this split node is expanding in original graph, because split graph and original graph are basically the same. You just really split things. Yeah. Okay. Questions? Is it clear? Like, okay. Okay. So what do we have now? We get that wait. We get that we can, given any separator, we can compute expanding balance separator or shrink it in time something like log square max flow. And given this, now you can compute expanding the balance separator in like whatever this time is times log n. Okay, good. So we're done. And one possible project, by the way, is to do this thing in directed graph. So far, I didn't talk about directed graph yet, but like, yeah, you can define, like I will talk about it like maybe in 3 weeks, but this is a good project actually. It's gonna be useful, but just try to do this thing, like kind of emulate everything that we have learned, how to compute this one, and just make it work in the directed graph. Because this is not known, but I just believe that whatever you have learned here, just gonna generalize. Yeah. But it's not there.